Welcome, architects and engineers. Today, we're diving deep into one of the most critical and complex topics in SaaS development, multi-tenant system architecture. We'll move beyond the basics to explore robust patterns for isolation, performance, and security. The goal isn't just to build systems that work, but to build systems that are resilient, scalable, and secure by design, protecting both our users and our business from costly mistakes. Let's get started. In 2019, Salesforce experienced a data leak that cost them $47 million. It wasn't a sophisticated hack. It was a simple query that accidentally crossed tenant boundaries during a routine maintenance operation. This incident was a wake-up call for the entire industry. It revealed that even a minor flaw in tenant isolation can lead to catastrophic consequences. This isn't just a security failure. It's a fundamental architectural challenge. Today, we'll dissect the patterns that prevent these disasters, ensuring the cost efficiency of SaaS doesn't come at the price of security and trust. At the core of multi-tenancy lies a fundamental decision about data isolation. There are three primary patterns, each with significant trade-offs. First, the shared database shared schema model, where all tenants coexist in the same tables identified by a tenant ID. Second is the shared database separate schemas model, which provides a logical barrier within a single database instance. And third, the separate databases per tenant model, offering maximum isolation. This choice is not purely technical, it's a strategic business decision that directly impacts your unit economics, your compliance capabilities, and the velocity of your engineering team. We'll now examine each of these in more detail. The most common and resource-efficient pattern is the shared database shared schema model. Here, every tenant's data resides in the same set of tables, and we rely on a tenant ID column to distinguish between them. In this approach, every single database query written in the application code must include a where tenant ID equals clause. While this seems straightforward, it introduces a dangerous single point of failure. A single missing where clause, one forgotten filter in a complex join or a background job, can expose one customer's data to another. This is precisely the type of failure that led to the Salesforce incident. It maximizes resource utilization, but also carries the highest intrinsic risk of cross-tenant data exposure. To mitigate the risks of application layer filtering, we can push the security boundary down into the database itself using features like PostgreSQL's row-level security, or RLS. Instead of relying on developers to remember the where clause every time, we define a security policy directly on the table. This policy automatically appends a filtering condition to every query executed by a specific role. For example, a policy can enforce that queries only return rows where the tenant ID matches a value set in the current session. This creates a powerful safety net. Even if the application code has a bug and omits the filter, the database enforces the tenant boundary, preventing a data leak. Netflix uses a hybrid model like this, applying RLS for critical data while using application filters for less sensitive operational data, balancing security with performance. Isolation isn't just about security, it's also about performance. The noisy neighbor problem occurs when one tenant's workload consumes a disproportionate amount of shared resources, degrading performance for everyone else. Slack's infamous 2020 outage was a prime example of this. Two powerful patterns to combat this are connection pool segregation and resource limiting. Instead of a single shared database connection pool, we can create separate pools tiered by tenant plan. For example, larger pools for enterprise customers and smaller ones for basic users. Furthermore, implementing tenant-level resource quotas and rate limiting using algorithms like the token bucket ensures that no single tenant can monopolize CPU, memory, or API requests, guaranteeing a baseline level of service for all customers. One of the most subtle but critical vulnerabilities in multi-tenant systems is context contamination. This happens when the application state from one tenant's request bleeds into another's. To prevent this, we must